which is why you can shine a laser to a mountaintop, and someone could be like, hey, I see a little red dot, or a little green dot, because they don't diffuse. It's one beam that doesn't spread out. It's called coherent monochromatic light. Yeah?
Could you make lasers in other colors if you wanted to?
Yes, absolutely. The hows and the whys of lasers, I would love to get into, but one, it's really complicated. Two, I don't entirely understand it all myself. And three, it requires an understanding of superconductors or semiconductors. So if you want to know how lasers work, there are some really cool YouTubes about how we can make different frequencies of lasers. It's pretty slick. So I would love to get into them. But right now, just realize lasers have a single beam. It's monochromatic, meaning one color, and it's coherent, meaning all lined up together. Yeah?
So how come it's harder to see when down onto the side of the road? It's hard to see on the road.
Because it's just you're bouncing off stuff. Unless you have a crappy laser that isn't very coherent. Like my green laser, its lens is garbage, so it makes like a big dot. On the screen it's like a small dot, in the back of the room it's like a big dot. The lens is garbage. Polarization. Oh jeez, I don't know what happened to my polarizing filters. So polarization is pretty cool. Realize that all light is vibrating in 3 dimensions all at once. So we tend to show light as a transverse wave, but it isn't really as we show it, because we draw a transverse wave on a 2-dimensional plane. That's problematic, because what it actually is a 3-dimensional phenomenon. Okay. There's one more place that my polarizing filters might be. So understand that we tend to show a longitudinal wave like this. But that's because we're drawing on a 2-dimensional plane. In reality, it's a 3-dimensional phenomenon, more like a corkscrew. Okay? So this is really more what's going on with light. But when we show it on a 2-dimensional wave, our 2-dimensional surface, it looks like that. Does that make sense? Okay. So it's vibrating in every direction. What polarizing does is it selects out one direction, one dimension, X, Y, or Z, and then it samples and says, I only want light that is vibrating in that direction to be seen. Well, I have my small ones. We'll have to do that. I was given some big, fat polarizing lenses, polarizing film last year. I still have my small ones. I don't know what happened to the big ones. All right. Let's try this.
So is that why that thing that blocks out TV screen?
Yep. Because it's only polarized in a single direction. So again, I don't know where my big ones are. I'll task Ms. Wagner to go find my big ones in the back. Go through everything and find it. Just joking. So this is a polarizing filter, and this is a polarizing filter. These are identical pieces of plastic. And watch what happens when I overlap them. Okay, see this? You see how they're let me find something white. You see how they're overlapped right here?
Yeah.
Watch what happens when I turn this one 90 degrees.
Whoa.
Will that do it? Because let's say this one is oriented vertically. Then only the light that comes through vertically passes through this one. And let's say this one is also oriented vertically, then light travels through it again. It's kind of like 2 fences lined up. So you can have light that is vertically going through this one, and light that's vertically aligned going through this one. But the moment I turn this 90 degrees, this second filter is only allowing light to go through that is horizontal. How much horizontal light is passing through the first filter? None. So nothing can get through. Only vertical light's passing through the first filter, so only vertical light can go through the second filter if it's vertical, and none if it's horizontal. Does that make sense? Okay. I really wish I had big ones. So I'm just going to go ahead and have you, try not to touch the actual screens of the polarized because it's a very, very fine piece of plastic that's been etched by a laser. You can hold the edge and you can be like, hey, hey, so there you go. You can just try to hold only the edges. I feel really bad because I got these big 10-inch pieces that somebody gave me last year and I've completely lost them. Okay, any questions about polarization? Yeah.
So what did you summarized it before you showed us those filters? What did you say it like seeks out one direction or?
Okay, so the polarizing filter is like a gate, like a fence, and the fence posts are vertically aligned, so it only allows light that comes in vertically aligned. It turns this into this.
So
now,
only vertically aligned light passes through.
Exactly. Now, if I take another fence and also vertically align it, then the light will go right through the second fence. But if the second one is tilted 90 degrees, then there's no light that can get through because I've only allowed vertically aligned light to get through. Does that make sense? Yeah. Okay. So how is this used? Yeah.
Is this what like the stuff on your car windows is?
Yes, exactly right. So polarizing film, like that, if you get good, qualify this, if you get good tinting on your car, it should also be polarized. It shouldn't just be a bunch of material that is dark. It should also be polarized. You know it's polarized if you put on a set of quality sunglasses and there's little colors all over your windows. You know what I'm talking about? Yeah. Like you see some like tinting and there's like rainbows on the windows. Those rainbows are from the interaction of the two polarizing filters. Some from the filter that's on your car window and some that's on your glasses. If you don't have that, then your tinting was cheap. All right. Where all it's doing is just reducing the amount of light. The good tinting, you want light to come in this way. Okay? You want light to come in like basically perpendicular to the film. Does that make sense? You don't want the light to come in vertically because light that comes in vertically is going to be sunlight that heats up your car. And no one's going to be like, what's going on in the sky? What we care about is what's going on perpendicular to the window. Does that make sense? So the good filters will be polarized perpendicular to their plane. So the light going in and out of the window you can see easily, but the light coming down from above you can't see because it'll get blocked. Make sense? Yeah. Again, if you put on really high quality sunglasses which are almost always polarized, and your parents' filter, look, you can see like a rainbow effect, then they got a good quality filter. If you can't, then you kind of got ripped off. So, okay. Any questions before we move on?
They're all going to check this out this week.
Yeah, hopefully, yeah.
All of them.
So if it is like not completely like horizontal or vertical, it's like kind of tilted, would it let in less light or?
Yes, it lets in less light, and the actual reason for that, it has to do with the quantum effects of how light itself doesn't want to be lined up. So it tends to break the laws at the quantum level. And there's a really crazy thing. If you took a third filter and you put it at a 45-degree angle, it'll cause light to move through the second filter. It'll rearrange the light as it goes. But we're not going to go into too much detail about that because we're running out of time. Okay, Doppler effect. So just like with sound, light has a Doppler effect. If a source is moving towards an observer, the light appears to get squished and the frequency goes up, and we call that blue shift. It's moving away from the observer, well, the frequency of light gets stretched, and we call that redshift. Now realize, you cannot do this with a flashlight, unless you put a flashlight on like a missile and launched it at somebody. Because the light has to be moving extremely fast with respect to the speed of light. So the speed of sound is 340 meters per second. You can get a Doppler effect with a change of like 20 or 30, basically a tenth the speed. You would need a tenth of the speed of light to get a considerable Doppler shift. So what things do that? What things are moving that fast?
Galaxies.
Yeah, galaxies, exactly. Galaxies, stars are all moving that fast. So we can tell if a galaxy or a star is moving away from us or toward us
by the tiny little shift in its frequency of light. Who shifts redshift?
Do we see any shift from the sun?
No.
Nope, because we are moving perpendicular to its light. We're moving around in a basic circle, so we're moving perpendicular to its light, so we're never really getting closer or further away from the sun.
That'd be a bad thing if we were seeing shifts.
Yes. However, we can see a shift. How would we see a blue or red shift from the sun?
It going over the horizon.
We put a mirror on the moon. Because the moon is actually moving towards and away from the sun as it goes around the earth. So you put a mirror on the moon. Then we look at the mirror and like, oh, we're getting faster or slower as the earth. Because realize the earth is going around perpendicular, but the moon's also going around the earth, so we can actually put a mirror on the moon and like, hey.
Didn't they put a mirror on the moon when they were?
That's the rumor, yeah. Yeah. One of many experiments are like, just put something like that. Okay. I would imagine we could use the surface of the lander that's still there as a target too. Okay, so dyes and pigments. Yeah. If you don't get dyes and pigments right away, that's okay. The biggest difference between a dye and a pigment is a dye subtracts one color or subtracts some color and lets the rest go through. A pigment subtracts some color and holds on to it and reflects the rest. But they do the same thing. A green dye grabs onto the red and lets everything else go. A green pigment grabs onto everything but green and lets green get re-emitted. Does that make sense? So, yeah. So pigments absorb some wavelengths and reflect the rest, basically sends them out, and a dye absorbs some wavelengths and allow the rest to pass through. That's the difference between a dye and a pigment. Now, why are some useful? Pigments are opaque. Dyes are transparent. It's kind of fun. And when two colors are complementary, we basically say that the light they produce will produce white light. It's not true white light, but we can detect it as kind of like white light. I gave chemistry a huge project, but I'm not going to give you anything over the weekend. Well, somehow we're not going to get through 5 slides. 7 slides. We're almost done. Okay, discussion time. What color of light do most plants absorb? Okay, what is most of the color of light that most plants absorb?
Red.
Red,
Nice.
not green. Chlorophyll is green because it allows a lot of green to pass through it. Most plants absorb reddish light. Makes sense, right? There's not a lot of energy in red light. And this is one of those things that I struggle with. Why is it that God made plants chlorophyll green? It would be a lot more efficient if plants were what color?
Red.
Yep.
White.
Black. Yeah. If plants could basically absorb all the wavelengths of light, the plant would be black. It would have a lot more energy, but it's green, which means it absorbs reddish light. There's not a lot of reddish light in our spectrum. In fact, if you asked a computer what color the sun is, by the way, what color is the sun?
White.
White, right? Because the sun is a black body, so it's white. If you ask the sun what, so this is the spectrum, what color the sun is, you know what it would say? It would say it's green. Because we got green, yellow, orange, red, blue, violet, Roy G. Biv. So this is kind of what the distribution of light looks like for the sun. There is more green light coming out of the sun than any other color. So it would make sense that plants would be reddish. They can absorb the most color. There's really not very much red light coming out of the sun. Kind of weird. God, why'd you do that? Why do you hate plants so much? You could have more food if they were just black. You could absorb a lot more light. Okay, questions? All right, anyone ever sneezed on your phone or your computer screen?
Yeah.
That's what you see, right?
Yeah.
Yeah. So computer screens, phone screens, they have lots of green, blue, and red dots. I'm sorry, my screen makes the green look white because my projector is garbage. But they have little dots. Sometimes they're rectangles, sometimes they're triangles, sometimes they're squares, and sometimes they're round dots. But this is how light is made, because these dots mix up to produce light. Now, what are the three primary colors? Red, blue, and green, RGB. Okay. We're getting there. As our technology gets better and better, we're realizing that the primary colors are not red, green, and yellow. Or sorry, red, blue, and yellow, like they teach you in elementary school. They're red, blue, and green. So this is why RGB. We're going to do a lab with this concept. And the bell's about to ring. And the subtractive colors, you can go back and tell your kindergarten teacher, are red, blue, and yellow, but we call them magenta, cyan, and yellow. These are called subtractive colors. When you mix a primary color together, oh cool, this is the last slide, awesome. When you mix two primary colors together, you get a subtractive color. When you mix two subtractive colors together, you get a primary color. Wow. Yeah. You mix red and yellow, sorry, red and green, you get yellow. Red and blue gets you magenta, blue and green gets you cyan. On the other hand, if you mix yellow and cyan, you get green. And if you mix yellow and magenta, you get red. And if you mix cyan and magenta, you get blue. So this is what your phone is doing. This is what your printer is doing. Your printer is laying down pigments to make the primary colors, and your phone is emitting the primary colors to show an image. Pretty cool. Wow. Yeah. Let's see if my top has any speed left, or any battery bar left. Hey, look at it go. It's red. It's green. It's blue. Wow. And since there's a red, a blue, and a green LED, it's magenta. It's yellowish. Yeah. This is supposed to be white light, but my alignment's not great. Ooh, that's hot. Okay. Hey, it looks magenta again.